Okay, we're going to talk about something called limiting reactants. Now, we need to review a couple things about chemical reactions before we can really start talking about limiting reactant. Okay, in a chemical reaction, okay, I'm going to go back to this slide back here. In a chemical reaction, if I say we start with 100 grams of CaCO3, and let's say just for example's sake, it would form 40 grams of CaO. Right? I don't know that that's the case, but let's just say for example's sake, it does that. Okay? What this chemical reaction is telling me is that if I am able to break down all 100 grams of this reactant, if my reaction goes all the way to completion, right, which is the goal, if I break down all 100 grams of that, then I would maximum be able to make 40 grams of calcium oxide. We agree. Right? If I use up all of my reactant, then this is the most amount of product that I could make, okay, of that particular product. Now, I'm making up the numbers, but do we understand the idea of that?
Does that
okay?
mean CO2 have to be 60?
That's right, right? However, what happens if something stops our reaction, right? What happens if something stops our reaction? This is what a limiting reactant is. So let's just talk through the words limiting reactant, okay? Reactant means it's what I'm starting with, but limiting means that it's limiting the amount of product I can make, right? A limiting reactant says that one of my reactants is going to make my production stop. Okay, and so we're going to figure out what that is. So to introduce the concept a little bit more in an everyday type language, we use recipes to help us kind of envision what a limiting reactant is. So we're going to walk through this kind of recipe analogy, okay? Many cooks follow a recipe when making a new dish. When a cook prepares food, they need to know the sufficient amounts of all the ingredients available, okay? So we're going to look at the recipe for a cheeseburger here pretty soon. But what I want you to think about is, let's say I go to make cookies, right? I go to the kitchen to make cookies, and I need 4 cups of flour, right? The recipe calls for 4 cups of flour, but in my cabinet, I only have 3 cups. Can I make the full recipe? Can I make fully what the recipe intended? Yes or no? No, there's no substitutions I can make. I don't have any almond flour, okay? What else? Can I make fully what the recipe called for? Yes or no? No, I can't, right? My limiting reactant in that case is flour, because I'm going to run out of flour before I finish my full recipe. Okay, that's the overall concept of limiting reactant. So let's take a look at this recipe here, okay? I need a hamburger bun, I need a tomato slice, I need 2 slices of cheese, and 2 burger patties. That's what this recipe calls for the formation of this double cheeseburger. Now, cheeseburger toppings are, your own opinion, but this is what we're going with for now, okay? I would say no tomato if it were me, okay? But it's not me. If I want to make 5 of them, how many buns do I need? If I wanted to make 5, my recipe calls me to make 5. How many do I need? 5. How many patties do I need? 10. How many cheese slices do I need? 10. And how many slices of tomato do you need? 5, right? That's what the recipe calls for. The ratio stayed the same, didn't it? Right? 2 patties per 1 double cheeseburger. 2 cheese per 1 double cheese, right? All of the other things stay the same. The ratio stays the same, but the amount of product we could form changes. So let's say if I start with this, if I start with 1 bun, 2 patties, 2 cheese, and 1 tomato slice, how many total cheeseburgers can I make? 1, right? I've got the ingredients to make one of my product. We agree here? Okay, let's say that I start with 2 buns, 4 patties, 4 cheese, 2 tomato. How many of my full recipe, how many products can I make? 2. Okay, let's say I start with a mole of buns, 2 moles of patties, 2 moles of cheese, 1 mole of tomato. How many can I make? 1 what? I can make a mole of product, right? I have a whole mole of buns. This doesn't change anything. The ratio is still the same. So I've got 1 mole of buns, 2 moles of patties, 2 moles of cheese, 1 mole of tomato slice. So I can make a mole of my product. The ratio is all the same there. What if I start with 10 buns, 20 patties, 2 slices of cheese, 10 tomato? How many can I make? I don't think so. I can only make 1. Because what am I going to run out of? Cheese, right? I only have enough slices of cheese to make how many of my product? 1. So what's my limiting reactant there? Cheese, right? Cheese is my limiting reactant. It limits the amount of my product that I can make. Okay? It limits the amount of product that I can make. I need to make sure that we understand that concept. Right? I'm going to run out of cheese. Let's say I've got an assembly line. Buns, patties, cheese, tomato, right? After I make the first burger, I'm already out of one of my reactants. So my production comes to a stop. Right? There's nothing else I can do. So I can only make 1. Okay. We can't make any more than 1 double cheeseburger. Slices of cheese limits the reactions. Okay. If one of our ingredients gets used up during preparation, it's called the limiting reactant. You will see me abbreviate that with an LR a lot, okay? LR just means limiting reactant. Limiting reactant limits the amount of product we can form, and in this case, that was double cheeseburgers. It's equally impossible for a chemist to make a certain amount of product if a desired compound, if there isn't enough of the reactants. So let's say that our chemical reaction calls for 4 moles of something, but we only start with 3 moles of something. That means I can only make 3/4 of my product. Right? Do you see the relationship there? Let's say that the recipe or the reaction calls for 6 moles of something, but I only start with 3 moles of it, which means I can only make half of the amount of product my recipe or my equation calls for. Okay? Yeah.
But like there would still be like with the stuff that's like not the limiting factor, that would still be like leftover.
Bingo. Right? It would be leftover. That's called excess reactant. So you've seen in some problems, it says this much of my reactant plus excess sodium hydroxide or whatever. That means my other reactant's going to have some left over that just sits. Okay? So the reaction will stop. If I'm supposed to react 4 moles of hydrogen gas and 3 moles of oxygen gas, and I only got half of it, I'm going to have some oxygen left over. That doesn't do anything. Yeah, realistically, right? After your reaction is done, you're going to have this excess reactant left over. It doesn't move to the product side, though. It's just considered an excess reactant. Yep. All right. This says a mole of N2 reacts with 3 moles of H2 and 2 moles of NH3 are produced. Let me zoom that in a little bit. Are you seeing this on your slides?
Yeah.
Okay. This is the reaction for the formation of ammonia. It says when 1 mole of N2 reacts with 3 moles of H2, then 2 moles of ammonia are produced. So here's our reaction or our recipe, right? If you want to think about it like that, our recipe. So how much ammonia could be formed if we reacted 2 moles of N2 with 3 moles of H2? Okay, so the recipe calls for this, or the equation calls for this, but let's say I started with 2 moles of N2 and 3 moles of H2. How many moles of my product could I form? Right? You don't have to do the math necessarily. I just want you to check the ratios and see what you think. Raise your hand if you think you have an idea. How much of my product could I make if I'm starting with, the recipe calls for 1 mole, I'm starting with 2. Recipe calls for 3, I'm starting with 3. And then we're trying to find out how many moles of my product I could make. Okay. Raise your hand. What do you think? If you think you know. Keegan, what do you think? 2 moles of NH3. I would agree. Why is that?
Because it takes 3 of H2, you aren't given 6, you don't have that.
Yep. Bingo. Okay. How many of you were thinking like, well, duh, you'll be able to make 4 moles of that? right? You started with double, so I'm going to make double. That's not the case, right? I did start with double of N2, but my H2 is all going to be used up within the first mole of N2 being used. Okay, so H2 in this case is my limiting reactant. So I'm still only going to be able to make 2 moles of my product. And then that means I'm going to have 1 mole of this substance left over. That doesn't react with anything, right? It does not get used. I'm going to use up 1 mole of N2, because that's what the recipe calls for, with 3 moles of H2 to get my product. Okay? What if I had... let's see, what if I had started with 4 moles of N2 and 12 moles of H2? How much product could I make? If I started with 4 moles of N2 and 12 moles of H2, how much here can I make? What do you think? Say it. 8 moles. 8 moles. Look at the ratio there. I'm starting with 4 times as much as I need. This one's also 4 times as much as I need. So I'm going to make 4 times as much product as it called for. Do we see the ratio there? Yes or no? Okay. Now, the difference with what we actually are going to start looking at is very rarely are they going to actually give you nice, pretty whole numbers to work with, right? We're going to have to work with grams. But we're going to be able to examine the amount of product we make to help us determine what our limiting reactant is. Okay. That's just me talking through that. All right. We're going to try this reaction. What is our limiting reactant when 82 grams of copper? Oh, goodness. What's our reaction when 82 grams of copper reacts with 25 grams of sulfur? What's the maximum amount of copper sulfide that can be formed? Okay? So when we do limiting reactant problems, the actual reality is that when we're given grams, it's harder for us to compare how much product we can make, right? It's not an easy thing for us to pick out. So when we do this, we need to do the problem twice to find which is the limiting reactant. Okay, it says do the problem twice. To find which is the limiting reactant, look for how many grams of the product can be formed from each amount of reactant. That means we're going to have to do a T-chart that goes from grams of copper to grams of copper sulfide. And then we do another one that goes from grams of sulfur to grams of copper sulfide. And we're going to compare which of those allows us to make more product, or in other words, which of those limits the amount of production we can make. Okay? So let's start with that. We're going to do 2 different T-charts here, okay? The way we know we're going to have to use 2 different T-charts is it gives us 2 different starting amounts. Okay, it gives us 2 starting amounts. So that's how we know we're going to have to do 2 different charts here. So let's go ahead and start with that. These are both gram to gram. You need out your periodic table. You need out your calculator. All of those things to solve. I'm going to start with our 82 grams of copper. I'm looking for grams of copper sulfide.
Is this where you not allowed to just add the bone masses?
Nope. I will tell you, we'll get to a little bit later being able to speed this up a bit, but maximum amount of copper sulfide, we want to go ahead and find that in grams. Okay, later I'll give you some shortcuts that maybe go with that, but for right now we're going to go grams, okay? So we're going to go grams of copper to all the way to grams of copper sulfide. So that means I'm going to go grams of copper to moles of copper. Moles of copper to moles of copper sulfide. And then moles of copper sulfide to grams of copper sulfide. Okay, so go ahead and work that out. Put your numbers in there. Moles gets the 1 here. We didn't check to make sure it's balanced, but I see a coefficient, so I assume that it is, right? If you look over it, it actually is balanced. So that's going to get a 2 and a 1. Moles here gets the 1. Copper sulfide, 55. What'd you get? 159. Okay, thank you. 159 or 160, somewhere in there. Okay. Copper needs to stay at 63.5. So I don't know if that needs to be adjusted or not, but okay. I've canceled grams of copper, moles of copper sulfide. I'm left with grams of copper sulfide, which is what I want. And that gives me, I don't know, tell me what we got for our grams of copper sulfide product there. 102.66. 102. Okay, thank you. Oh, that's hard for you guys to see, sorry. One 102.66 grams of copper sulfide. Let's do the next one now. Okay, we've got to go from grams of just pure sulfur to grams of copper sulfide. And this time we're starting with 25 grams of just sulfur. Grams of sulfur to moles of sulfur. Moles of sulfur to moles of copper sulfide. And moles of copper sulfide to grams of copper sulfide, right? We already calculated molar mass, so that's going to be easy for us. We're comparing our amount of product, so we want to make sure we take it to the same product both times, right? Here we only have one product, so that's all we can do. But that's going to come into play later. Okay, we're just doing sulfur. So I'm going to guess it's going to be higher than the first one. Give me your mass of copper sulfide here that's been formed. Say it louder. 124.22 grams of copper sulfide. Now, tell me, do we all agree on the T-chart numbers? Is that what we had when we plugged it in? Yes or no? Yes. Okay. So here's where the important part happens. Okay. We've established that if we use up all 82 grams of copper, then we would have the ability to produce 102.66 grams of copper sulfide. Then we understand that part of it. Right? If all 82 grams of copper gets used, we would potentially, right, we have the potential to produce 102.6 grams of copper sulfide. Now, on the other side of that, if we use up all 25 grams of sulfur, we have the ability to produce 124 grams of copper sulfide. Now, is that going to be possible? Is it possible for us to produce 124 grams of product if we just set up here that our maximum amount is 102 grams? No. So that means we're going to use all 82 grams of copper and we're going to produce 102 grams of our product and then our reaction stops. So we're not going to have the ability to use up all 25 grams of our sulfur. We're going to have some of that be left over or excess.
So would you just subtract to find the excess?
We don't have to, okay, so if we were going to find out how much sulfur was left over, we would have to do another T-chart, right? So we're not going to talk about that right now, but that's a good thought, right? We'll use that later. So we're not going to have the ability to use up all 25 grams of that, and we would never reach the point where we could produce all 124 grams of what's expected. So that means the maximum amount of copper sulfide that could be formed is 102 0.66 grams. That is the maximum amount. Because we're going to run out of copper before we get to the point where we can produce 124 grams. Yes?
Will we need to do like a percentage of how much sulfur is?
Nope, not yet. Eventually we'll get to the point where we can calculate how much sulfur is left over, but we're going to get good at this part first. Okay? So that means if it asks me what is my limiting reactant, am I going to say that copper sulfide is my limiting reactant? Is copper sulfide a reactant at all? No, I'm going to come back at my T-chart and say copper is the thing that's getting fully used up. So that's my limiting reactant, right? I'm going to use up all 82 grams of copper, and then once I'm out of copper, my reaction stops. So copper is my limiting reactant here, right? My limiting reactant equals copper. Now, we don't just circle this part and say that's our limiting reactant. We would either rewrite it or we'd come back and point at the reactant part. But we'll talk about that as we go through the next couple of days of our lesson there.